Welcome to this lecture in our course on mechanical operations. In the last class we talked about storage of particulate materials, and we particularly looked at how pressure distribution developed within a particulate mass. So, we will continue that discussion, and also we looked at some pictures of what industry scale bins and silos and hoppers look like and how they operate, some of the problems associated with them and how they can be overcome in the design and so on. So, in today's lecture we are going to look particularly at bin storage and why do problems occur with discharge out of bins, why do sometimes collapses happen like we saw in the PowerPoint. The reason for that is that solids again do not behave like liquids, okay. That is a key thing you have to remember all the time. When you have solid material stored inside a bin, as we have seen before, the applied pressure is not the same as the pressure in the other directions. In fact, the minimum pressure occurs in a direction that is normal to the applied pressure. So, in terms of bin storage, what does that mean? There is a pressure, let us say just atmospheric pressure, that is forcing the material from the top. It is almost like a piston that is forcing it down, and of course there is gravity also, but the pressure that is transmitted to the walls of the bin is actually less than the pressure that is normal to the material, right. So, you would think in general that is goodness in terms of at least the pressure that is on the walls of the bin, but the other factor to consider is that you do develop a frictional force at the walls as the particulate material tries to slide past the walls, and this actually is reflected on as a shear stress that can transmit through the entire particulate mass all the way into the bulk. And it is in fact this force that causes many problems to happen, particularly the arching problem that we saw last time, where material refuses to discharge from an opening at the bottom, and instead you form a kind of a bridge like structure which prevents material from moving down. So, it is clear that bin storage of solid materials is a very different challenge than storing a liquid in a container. So, let us look at that a little more closely in terms of how the pressure, particularly at the bottom of a bin. So, let us say that you have a circular bin with vertical slides and you have particulate material stored in this. The key is, what is the pressure on the bottom of the bin? That pressure is important because it does have implications for the discharge out of the bin, which is usually through the bottom. And by the way, the reason that material discharge is done through the bottom of a bin is because pressure is maximum at the bottom. If you try to do a side discharge, clearly the pressure, the lateral pressure, as we have seen before, is going to be lower than the vertical pressure, and so chances of clogging are much higher. So, one of the critical parameters here is, what is this value, let us call it the pressure at the bottom of the bin as a function of, let us say that this whole height is Z total. You would like to find this expression, and then you would like to compare this for liquids and for solids. And I will tell you as a preview that what you will find is, if you plot this height of the bin versus pressure at the base, what kind of relationship do you see will happen if you have liquid storage? Let us say it is a normal Newtonian liquid, something like this, right. Now, if you have particulates stored, what do you think will happen? Will it also look linear, or will it go like this, or will it go like this? Let us say this is 1, 2, 3. Which do you think is more likely? How many think 1, 2, 3? Actually 3 is the correct answer, but why 3? Anybody venture to guess? Because when you apply pressure to a particulate mass, it does not really transfer well to the bottom. A lot of it, see, actually think about it this way, when you have liquid and you apply pressure, you force it down, right. But if you have solid mass and you apply pressure, what happens to it? It actually compacts, right? You actually increase the local density. The bulk density parameter is the one major variable between liquids and solids. In a sense, you can look at a solid as a highly compressible liquid. So, the more pressure you apply, the more the particles interlock and the more difficult it is to get them to flow. But this, so the pressure that you are applying does not get reflected as a pressure on the bottom of the bin. If it did, it will actually help with the flow. Instead, what happens is a lot of that pressure gets distributed to the walls of the bin above a certain limit. In fact, once your ZT value exceeds 3 times the radius, let us say that this is the radius of this bin, this leveling off happens at this 3 times radius point. Once the height of your bin exceeds 3 times the radius, the pressure on the bottom levels off. No matter how much solid you keep adding, it will add to the weight, but it will not add to the pressure at the bottom. So, clearly all that added mass, the weight has to be taken up by the other surfaces that are in contact, and that is where buckling of columns and things like that happen. So, but where can we get an expression that gives you this type of behavior? I think you can do an analysis on this. So, let us take that you take a small section, some dz let us say, and you look at how, just do a pressure balance around that. So, let us say that here you have a pressure PV, vertical pressure or applied pressure, and this pressure here becomes PV plus some dPV, and let us say that there is a corresponding PL or lateral pressure that develops on the sides. Now, if you do a force balance, what do you have? You have FV being equal to FG plus FF. Actually, this will be a minus because the applied pressure and the frictional pressure are going to be opposing the gravitational force that is forcing the mass to move down. Or if you look at this differential element, dFV will be equal to dFg minus dFF, right. So, what is dFV? It is the area pi r squared times dPV. dFg is the gravitational force. So, that is equal to pi r squared times dz, which is the volume of the element, multiplied by the bulk density rho b times gravity. And what is dF frictional? Now, here you have to introduce a coefficient of friction, let us call that some mu prime times dFL, which is equal to mu prime times 2 pi r dz times PL. So, the assumption is this PL, the lateral force is uniform across this section dz. Okay. So, just do a balance. So, it says pi r squared times dPV equals pi r squared dz times rho b times g plus, or actually minus, mu prime times 2 pi r dz times PL. If you remember in the last lecture or 2 lectures ago, we had introduced this notation that PL over PV equals K prime, right. And so, you can substitute that here, also cancel out pi r and then integrate both sides. One side you integrate from 0 to z total zt, On the other side you integrate from 0 to Pb. Okay. So, integral 0 to zt of terms containing dz equals integral 0 to Pb of terms containing dPb, and you solve that, and that is when you get this expression. So, the relationship that you will get will look like this: Pb is equal to r times bulk radius times g divided by 2 pi mu prime k prime times 1 minus e to the power minus 2 pi mu prime k prime times z t over r, and this expression yields this kind of dependence. So, again r is the radius of the bin, rho b is the bulk radius, g is gravity, mu prime is a friction coefficient, k prime is PL by PV. The coefficient of friction is clearly a parameter here that you need to estimate, and the way you do that is by doing an experiment or by just observing at what angle do the solids that are in contact with the bin walls start to slide down, and if you take the tan of that angle, that gives you the skin friction coefficient. So, that is how you estimate mu prime. It is typically somewhere in the 0.2 to 0.35 kind of range. So, if you look at this expression, there are some interesting conclusions you can draw from it. If you look at Pb value, the dependence on r is somewhat complex, as is the dependence on nu prime and k prime, but bulk density is only in the numerator. It is in fact proportional to bulk density. So, clearly how well packed the mass is plays a huge role in terms of how easy it is to discharge, how much pressure builds up, and so on. Of course, k prime to some extent also reflects the material properties. As we have seen before, k prime can be a very small number for a highly cohesive kind of a solid, right. So, from this expression you can draw some conclusions regarding the effect of particularly the bulk density, but the rest of the dependence you will have to take a look at more closely. Now, what does this mean for us? Why do we care about pressure distribution? Why do we care about pressure at the base? Because all of it relates to the function. What you are trying to do is put material in from the top and take it out from the bottom, right. That is a function of a bin, and as I have said before, you want it to be a first in first out process. You want the material that you put into the bin first to come out ahead of the material that you put into the bin later. Now, in order for that to happen, what are some of the things you should do? Clearly, as I said before, an opening at the bottom is preferable to opening on the sides, because the pressure that develops is largest, but there are some other reasons as well. It turns out that if you have a side discharge, and if there is preferential discharge from one side compared to the other, you can start developing lateral forces and imbalances, and that can severely affect the stability of the bin. So, unless you can ensure at least approximately equal discharge from both sides of the bin, it is not a healthy situation. So, that is another reason to locate your hole at the bottom. Now, typically the holes are circular. Can you make the hole as large as the bin? Would that be the best thing to do? Do you think that will work? I mean, why should the opening be smaller than the floor area? I mean, I think it's an interesting idea, but you need a discharge that is as large and as wide as the bin. But what are you then doing? You are just taking it from one bin to another, right? So, it kind of defeats the whole purpose. So, what you need is a smaller opening with some kind of a control valve and so on, so that as needed you can discharge from the bin, preferably continuously. In fact, an ideal bin operation would be where the bin is filled in batches, but it is discharged continuously. There are two types of discharges that can happen. as I think we mentioned it briefly in the PowerPoint the other day. One type of discharge is where the entire inventory of material goes down together. It is called mass flow. The other type is where initially the discharge starts in the center and then slowly forms like a V and starts drawing in materials from the sides, so that the discharge starts in the middle and then slowly expands to include the other areas of the bin as well. The latter is actually more likely to happen. It is very rare that you see this mass discharge. The other type is called the tunnel discharge or conical discharge, and that is more likely to happen. The problem with that type of discharge though is, if something happens to break that cycle, then discharge can stop completely. For example, if you have highly cohesive solids, particularly those that are very sticky to the walls, then what can happen is you can start discharging through the middle. So, the first part will happen, but then instead of slowly spreading to the outer diameters of the bin, it will stop at a particular radius. Then you form something called a rat hole. It looks like a hole that has been dug out by a rat basically, and the material that is outside this rat hole stays where it is, never gets discharged. And in fact, particularly when you have a continuous charging of the bin, this material that is outside this so called rat hole may never get discharged. It may just stay there forever, and if you are not carefully looking at the inventory of material in your bin, you may never know it. So, some material could stay there for months or years and never get discharged, and then once in a while you will go and do something to improve the discharge, and you will get material out that has been there much longer than it should be, because most stored granular materials have a certain lifetime during which they can be used, and if you exceed that lifetime, there can be chemical changes that happen, there can be physical changes can happen, particularly if it is food stuff. There may be an expiration date that you have violated. So, that can all lead to fairly serious problems. So, bins typically do have mechanisms to make sure that does not happen, like as we saw in one of the animations, could be just a hammering where somebody goes around and hammers the bin once a day to make sure that any material that is accumulated to the sides gets pushed to the middle. Or it could have a vibrator attached to the walls, which will keep shaking loose any particles that try to stick to the wall, or it could be a jet that you blow in through the bottom to again make sure that material does not stick either to the walls or to each other, breaks loose clumps of material and makes it easier to discharge. Or it can be a simple physical device. Somebody could just go in with I don't know, some kind of a pointed metallic thing and just poke inside and loosen things. And these may sound crude, but if you look at the way industries operate, they actually have people doing this kind of thing. They have people walking around with large iron rods and poking inside a bin to make sure that the flow happens. But you can trace it all back to some very fundamental physical characteristics of the material. In fact, if you look at discharge out of a bin and you relate it back to the physical parameters of the bin as well as the material that is stored, it is interesting that there are only 3 or 4 parameters that really affects outflow from a bin. So, if you look at a parameter like m dot, which is the mass flow rate out of a bin, this is a function of really only 4 parameters. One is, assuming it is a circular opening at the bottom of some diameter dO, it is a function of dO. It is actually interestingly enough not a very sensitive function of either the radius of the bin or the height of the bin. The other 3 parameters that are important all have to do with the solid itself that you are storing. Any guesses on what some of these parameters could be? Would particle density play a role? that is not rho b, rho p. Rho b is a bulk density, which is an indicator of how well packed the particles are. Rho p is the density of the individual particle. How many say yes, rho p should be one of the important parameters? Rho p is because it is related to mass flow rate, right. I mean just volumetric flow rate multiplied by density gives you the mass flow rate. So, it is an important parameter, but only for that reason. What else? Do you think rho b is an important parameter, the bulk density? It is an important parameter, but interestingly enough it does not enter directly into the equation, but indirectly. How about particle diameter? Do you think that is important? In other words, do you think fine particles will flow differently from coarse particles? Because it affects a lot of things including cohesion and so on. Just one more, which actually does reflect on the bulk density to some extent, the packing intensity and so on, and that is this alpha m parameter. You remember we discussed 2 weeks ago, it is the angle of internal friction. It turns out that that is a very important parameter in dictating the flow of, okay, there are some constraints here. This mass flow rate refers to flow of granular materials, not highly cohesive material. I mean it will not, for example, if it is flowing wet cement, this will not be a good impression. So, it has to be a granular material like sand or food grains and so on. It has to be gravity discharge, we are not using any centrifugal or any other types, or by the way vacuum discharge and pressure discharge are other mechanisms that are used if you want to speed up the discharge, and obviously you are taking it out of a circular bin. So, this is the functional expression, and in fact there is an empirical correlation which says that this is actually equal to rho p times dO cubed divided by tan of alpha m, or k1 times tan of alpha 1 plus k2 plus dp plus k3 plus k4. K's are all constants. This is only valid in British units. So, m dot is in pounds per minute, rho p is in pounds per foot cubed, dO is in inches, and dP is in inches. Okay. Under those conditions this correlation is valid. Actually sorry, this is not dP, in general it is rho p times dO to the power n. This n can vary from about 2.8 to 3.2 depending on how cohesive the material is. For material that is less cohesive, which is free flowing, it depends as dO cubed, whereas for material that is a little more sticky, it goes as, the stickiest material goes as 2.8. So, again from this expression it is obvious that, I mean m dot by rho p is the volumetric flow rate, right. So, it is really, if you want to look at volumetric flow rate, it is simply dO to the power n divided by these parameters. It is interesting that in this expression dP is at the bottom, which would seem to indicate that material that is smaller would tend to flow through faster from a circular hole. Is that true in general? No. I mean if it is, if the size reduction is led to cohesive conditions, this is not true, but remember what I said, that this applies only to the flow of granular material. So, the assumption is this applies for cases where the particle size is dropping, but not to such a level that you have to start worrying about the increased cohesion in the solid material. the interesting thing here is you do not see any dependence on PB, right. But again, this is a pretty empirical correlation, and as all empirical correlations are, it has limited applicability. Suppose you were constructing a bin, I would not advise you to take this correlation as the gospel truth and design your bin based on this. You should do your own experimentation and assess whether it is true that some of the parameters that we do not have here, like total height of the bin, radius of the bin, pressure, that they really do not have an effect on your flow discharge, because the experiments were done on certain types of powders and materials that are stored in certain types of bins, and it may be difficult to extrapolate that the conclusions that you draw from this and apply them to a wide variety of cases. Again, as with most mechanical operations, there is no fundamental theory here. This is not based on any quantum theory or kinetic theory of molecules, that this is how things will flow or this is how things will discharge. It is based on people doing a lot of experiments, collecting a lot of data, developing a lot of empirical correlations and validating them. But the next time somebody does the same experiment, they might get a totally different result. That is a problem with any empirical relationship that you derive based purely on experimental observations. So, let us say that you have stored material and you have taken the material out of the bin. What is the next step in the process? It is conveying, right. The material has to be taken from wherever it is discharged to the next location in the process. So, another topic that is covered quite widely in mechanical operations textbooks and so on is this whole business of conveyance. How does material get transported from one step in your process to the next step? Now, I mean, essentially there are two methods. One is a batch conveyor, the other is a continuous conveyor. A simple example of a continuous conveyor would be where there is a conveyor belt. So, the material offloads from the bin into a container that is riding on this moving belt, and it just gets taken from one place to the other. So, that is one way. Increasingly, if you look at modern factories, this type of continuous conveyance is being employed, particularly where you have to keep production on 24/7. But if you have the luxury of being able to do in batches, a batch conveyor is certainly in many ways cheaper, less risky, because with a continuous conveyor the problem is if it breaks down, then your whole production could be affected until you get it fixed. So, you are kind of at the mercy of proper maintenance of your conveyance equipment. Environmental protection becomes important, because depending on the nature of the material you are handling, exposure to the outside conditions may or may not be okay. So, if you need to have protection against temperature and humidity or other impurities, then this whole conveyor has to run in a tunnel, where the tunnel provides an enclosure that keeps unwanted material from getting mixed in with your product material. Whereas a batch process can be run under much more controlled conditions. So, out of this bin you can take the discharge into smaller containers, and then just could have wheeled things. You can just wheel them from one place to another, from one step in your process to the next process. So, typically the batch conveyors are built for that type of movement of relatively small quantities of materials in processes where you do not need to keep the process running 24/7. There are many types of conveyors that are used both in the continuous case as well as in the batch case. A new wrinkle that is coming into this is robotic conveyors. Also known as pick and place robots. A robot can be trained to, a robot is not a humanoid robot, that is what you are imagining. It could be just a mechanized device which simply takes material from one place and places it in another place, right. These types of mechanical or mechanized, semi-automatic or fully automated kind of robotic machinery are becoming of increased use in process industries, primarily because they can be, they can be relied upon to do the same thing over and over. Anytime you involve humans, there is always the scope for variability. So, what is conveyed one time versus the next time, there will be differences. No human being can do the same operation identically one time to next, it's just impossible. Whereas a robot will do the same thing over and over and over, just its pluses and minuses. Human being, for example, if you are working with a bin, if they see something that does not look right, they will stop the process, right. A robot, unless it also comes coupled with a vision system where it can actually look at the material and decide if it is of appropriate quality and so on, won't know. So, it will just keep running the process until it is too late. So, there are advantages and disadvantages to going to the fully robotic route, but certainly from a consistency, uniformity of product, robots are hard to beat. But one thing that helps in terms of conveyors is to always use gravity to help you. So, in other words, if you have a bin and you need material from the bin for your next process, preferably the bin should be located at a height at some elevation above your next process step, so that material can discharge using gravity. As far as possible in a process industry, you do not want to fight gravity, you want gravity to aid you, and this is particularly true for storage and conveyance of materials. You never want to get into a situation where you load and you unload from the top. That is kind of the worst case scenario for a process, because that leads to essentially last in first out kind of handling, FIFO versus LIFO. First in first out is good, LIFO is bad. So, that is a cardinal message in storage and handling. If you have set up your process so that material gets continuously fed from one side and it gets taken out from the other side, and you can ensure that whatever goes in first comes out first, you got the storage problem solved essentially. But the thing is, when you want to discharge from the bottom, as we have said, there is going to be a resistance to flow, and this resistance will typically be seasonal as well. Especially in a large factory, how material gets stored and discharged during the hot and humid season would be very different from how it gets discharged during the dry and cold season. And so, there are many challenges. If some of your processing conditions change, the nature of your particular material might change also, from being less cohesive to more cohesive and so on. So, you do not want to make the problem worse by having to, for example, if you have to take the material from here and your next process step is at some elevation over here, how do you, now you have to pump, right, or figure out some other way of conveying the material. And if you think storage and outflow of particulate slurries is hard, pumping is even harder. It's very, very difficult to do, because as I said before, pumps rely on developing a pressure to discharge the material, but solid slurries do not react to pressure the way liquids do. In fact, they can get more difficult to discharge as you increase the pressure, as I said before, because you can press the particles against each other and cause them to lock with each other. So, you really do not want to pump liquid particulate slurries. So, as far as possible, try to use gravity to help you, or inclination. Make sure that even if you are not able to discharge vertically down, at least provide a slope and try to slide the particles, the material down that way. So, wherever possible, think of ways in which you can reduce the time involved as well as the amount of force that you have to apply, because it all corresponds to energy, work and energy, right. And just like with any mechanical operation, the real challenge is how do you get the work done with minimum investment of energy, because most mechanical operations are brute force kind of techniques, whether we are talking about size reduction or whether we are talking about storage and handling or conveyance. You could apply a lot of energy and get it done, but what you have to watch out for is, are you doing it the smartest way? or you're optimizing it, or you're applying minimum force, minimum energy, minimum time to get the work done, and minimum resources, because many mechanical operations are also labor intensive. So, the real challenge is not just to get the operation done, which is because these are simple operations. It's simple to reduce size, it's simple to store material, it's simple to take them from one place to another. But if you want to run a profitable operation, you always have to be thinking about, am I doing it the best way? Am I optimizing all the resources that are available to me, including human resources as well as energy and space and so on, and that is where your challenge as a chemical engineer comes really. Okay, so we will stop at that point. In the next class we will talk about another mechanical operation that is of a lot of importance in industry, and that is mixing of materials. Any question on what we have covered today? Okay, see you in the next class.